We have an example problem here. The electron gun, okay, with a typo. So, electron gun is to accelerate electrons from rest to 3 × 10⁷ meters per second within a distance of 2 centimeters. So, two questions. A, what electric field is required? And B, how should the electric field direction be oriented relative to the motion of the electron? Okay, the typo is because I had to remove the words in a TV because we don't have the old school TVs that have the cathode ray tubes anymore. And I didn't proofread when I removed that portion. So I apologize for that. So we have electrons. On my drawing right here, I'm just going to say they're moving to the right in my picture. They start at rest and accelerate to, this is meters per second, so a V final of 3 × 10⁷ meters per second within a distance, so delta S, of 2 centimeters. So we want to find the electric field required, and we'll have to assume just this average electric field because we need to assume a constant acceleration in order to relate our velocities and positions together. Okay, so I know there's an electric force on these electrons because they are moving in an electric field, and we're trying to find that electric field. That is the only force that we're worrying about right here, so that net force is equal to ma. We want E, we know Q, we know M, because these are electrons. These are values we can look up easily. So we actually need to figure out what the acceleration is in order to come back and solve for this electric field. Okay. The acceleration is going to come from looking at the motion itself. We have an initial velocity, a final velocity, a change in position. If I look at the kinematic equations that have these variables and acceleration, because that's what I need ultimately, that third one, the final v squared equals the initial v squared plus 2a delta s. Initial v is 0, and so a, our acceleration, will be v final squared over 2 delta s. So 3 × 10⁷ squared over 2 × 0.02. We need that in meters for this acceleration to be in meters per second squared. So I'm getting 2.25 times 10⁻⁻16 meters per second squared. Huge acceleration. That acceleration cannot last for very long because the electrons would quickly reach relativistic speeds, and then you have to start using relativity equations instead of Newton's equations. But again, in 2 centimeters. So this is a very fast time. It happens very quickly. Okay. Coming back in, the mass of an electron, 9.11 times 10⁻⁻31 kilograms. We've just calculated the acceleration the charge on an electron, 1.6 times 10 to the negative 19. And it is a negative charge for the fact that it is an electron. I'm getting 1.3 times 10 to the 5th. There is a negative sign just because that charge is negative. But again, negative signs here have to do with direction. So my answer to part A, it doesn't make sense to put a negative. I can only give the magnitude. There's no such thing as just a negative field. Negative has to do with a coordinate system and thus a specific direction. What the negative sign has to do with is that the electric field needs to be opposite the force. So in my picture, the force is what's causing these electrons to move to the right. The negative in my answer is telling me that the electric field then has to point to the left. So part B, how should this electric field direction be oriented? The electric field needs to point opposite. Opposite the direction of motion. The electric field is opposite the electric force when we're talking about the force on an electron, on a negative charge.